Good morning to everyone. Myself, MDD-II, Assistant Professor at Dr. Kamal Institute of Engineering and Technology. Today we will start our 5th lecture on machine design and drawing tool. In previously, we can concluded 4 lectures, and last lectures we can see the numerical on combined twisting and bending moment, sharp subjected to combined twisting and bending moment. In first unit, we are start with first one is design of shaft. In design of shaft, first lecture we can concluded shaft subjected to twisting moment only, then shaft subjected to bending moment only, then introduction of shaft subjected to combined twisting and bending moment. Then we can discuss about the numerical on shaft subjected to combined twisting and bending moment. And today we are start the 4th one. It's your design of shaft on the basis of rigidity. Design of shaft on the basis of rigidity. Design of shaft on the basis of rigidity. Okay. Then, in the types of rigidity, there are the 2 types. In the types of rigidity, there are the 2 types. First one is the torsional rigidity. First one is the torsional rigidity, and the second one it's your lateral rigidity. Second one is lateral rigidity. Okay, that's clear. In design of shaft, on the basis of it, there are 2 types. First one is the torsional rigidity. Second one is the lateral rigidity. Then we can see the first one. First one is torsional rigidity. In the torsional rigidity is the important case of the camshaft. In the case of camshaft of an IC engine, we can see the IC engines. In the IC engine, there are the camshafts, and torsional rigidity is the most important part at the time of your camshaft on the IC engine, where the timing of the valves would be affected. Whenever the piston can move from TDS to BDS, means top to bottom side or bottom to top side, at that time your camshaft can move their rotations. On that place, the timing of the valve are affected. So, where the timing of the valve would be affected, the permissible amount of twist should not be exceed 0.25 degree per meter length of such shaft. That's clear. It means at the time of IC engine valve, the permissible amount of twist should not be exceed 0.25 degree per meter length of the shaft. And for the line shaft or transmission shaft, at the time of transmission shaft, deflection is 2.5 to 3 degree. Then at the time of your transmission shaft, the deflection is 2.5 to 3 degree per meter length. 2.5 to 3 meter degree per meter length may be used as limiting wall. Okay, it's known as the limiting wall because as per the deflection, they are maintained 2.5 to 3 degree deflection. So it's the limiting wall. The widely used deflection for the shaft, is limited to 1 degree in the length, limited to 1 degree in the length, equal to the 20 times diameter of the shaft. It means when they can deflect that 1 degree in a length of meter, 1 degree in the length equal to 20 times the diameter of the shaft. When you design the shaft, you can calculate the small d, the 20 times of this diameter of shaft. Okay, and that is called the deflection of shafts. Then the torsional deflection may be assumed. The torsional deflection may be assumed in the equation. I think we can start here with the deflection formula. Do you know the torsional deflection by using the torsional equation? So what is your torsional equation? In torsional equation, that is T by J, it's T by J equal to G theta upon L. T by J equal to G theta upon L, or you can say that it's a theta. It's a theta equal to TL upon JG. TL upon JG. It means the torsional equation is T upon G equal to G theta upon L, or theta equal to TL upon JG. Okay, then what is the theta? Where theta is a torsional deflection or angle of twist. Then angle of twist in radian. Okay, we are given in suppose in degree, so we can convert that in radian. Then the T, theta is the deflection, torsional deflection. Then T is the twisting moment or torque on the shaft. That is your T. Then J is the polar moment of inertia of the cross sectional area about the axis of rotation. Okay, because as per the angle of axis angle, it depends on the cross section. Maybe it will be changes as per the diameter of the shaft. So what is your J? J is the polar moment of inertia. So J equal to pi by 32 into d to the power 4. Pi by 32 into d to the power 4. As well as the J equal to pi by 32. J equal to pi by 32 into d to the power 4 minus di to the power 4. Then first J equal to pi by 32 into d to the power 4. It's for the solid shaft. That is for solid shaft. And the J equal to pi by 32 into d to the power 4 minus di to the power 4. That is for the hollow shaft. That is for hollow shaft. That's clear. First here for the solid shaft and second here for the hollow shaft. Done. G is theta is covered, T is covered, J is covered. Second one is the G. G is the modulus of rigidity for the shaft. G is modulus of rigidity for the shaft. Then L is for the length of the shaft. L for the length of the shaft. Okay. These all are for the torsional rigidity. And at the time of design of shaft on the basis of rigidity, any problem is given, you can calculate as per this formula. Then second one. Second one is lateral rigidity. Second one is lateral rigidity. Okay, then the lateral rigidity. It is important. It is important in case of transmission shafting, and the shaft running at high speed. Whenever you can assume any shaft and the speed is increases, it means the shaft running at high speed, where the small lateral deflection, would cause the huge out of balance force. Okay, you can see any shaft whenever the shaft running speed is very high. At that time, they can vibrate. Okay, we all are noticed that whenever any shaft or any product speed is increases, then they can vibrate. At the time of vibrate, they can use out of balance force. Okay, then the lateral rigidity is also important for maintaining proper bearing clearance. You see your ceiling fan at the time of bearing is on the repair conditions, that time your ceiling fan is vibrating. Why they are vibrating? Because they are not a proper bearing clearance. So the lateral rigidity, it is used for maintaining the proper bearing clearance and the correct gear teeth alignment. At the time of gear meshing, they are also you can operating the fluctuating with the gears. They are also vibrating. They are also the huge out of balance force. That time also the use of your lateral rigidity. Okay, for the correct gear teeth alignment, it's used for the correct gear teeth alignment. If the shaft is uniform cross section, then the lateral deflection of a shaft may be obtained by using the deflection formula. As the strength of material. But when the shaft is variable cross sections, maybe someone it's very less diameter, many time it's medium diameter, and any time it's a huge diameter. So it depends on the cross sectional area. It depends on the variable cross sectional area. Okay. Then the lateral deflection may be determined from the fundamental equation for the elastic curve of beam. They can form with the help of your elastic curve of beam. Then, what is the elastic curve of beam? They can use by using the formula d square y upon dx square equal to m upon ei. So at the time of lateral rigidity is used for the at the time of your vibrating when you are vibrating, the shaft is running at very high speed. At that time they can vibrate, and at that time we can use the lateral rigidity. Okay, so that time the cover the introduction of your design of shaft on the basis of rigidity. Now we can taking one problem related to this one, and after that we can so now we can stop here for the theory and just we can start with the problem. So now we can start the problem on your design of shaft on the basis of rigidity. Okay. So first you are the write down the problem related to your design of shaft on the basis of rigidity. So, write down the problem. A steel spindle transmit 4 kilowatt. A steel spindle transmit 4 kilowatt at 800 rpm. 4 kilowatt at 800 rpm. The angular deflection should not exceed 0.25 per meter of spindle. 0.25 per meter of spindle if the modulus of rigidity for the material of the spindle is 84 gigapascal. Find the diameter of the spindle and the shear stress induced in the spindle. Okay. So we can calculate the diameter of the spindle as well as the shear stress induced in the spindle. Okay. I think first we are write down the given conditions. So as per the problem, first one is given is 4 kilowatt. 4 kilowatt, it means your power is to P equal to 4 kilowatt. 4 kilowatt, it means it's a 4000 watt. Then next one is given is speed. Speed is your 1800 rpm. So N is 1800 rpm. Then next one is given as 0.25 per meter length of spindle. So the theta is 0.25 degree. And we have already discussed that we have converted that degree to radian. Okay. So for that 0.25 into pi by 180 to the pi by 180. So the value of your 0.25 into pi by 180, it's your 4.363 into 10 to the power minus 3. 4.363 into 10 to the power minus 3 radian. At that time, we can convert that theta to radian. So theta is 4.363 into 10 to the power minus 3 radian. Then L. They can given as per meter length of spindle. So L is 1 meter. L is 1 meter. It means 1000 millimeter. Okay. Then next one is given as G, and G is your 84 gigapascal. So G is equal to 84 gigapascal. 84 gigapascal. It means giga means 10 to the power 9. So 84 into 10 to the power 5 Newton per meter square. But remember, we are required the diameter of spindle or diameter of the shaft in mm. So we can convert it that it's Newton meter to Newton per mm square. So it's 84 into 10 to the power 3 Newton per mm square. That's clear. So G equal to 84 into 10 to the power 3 Newton per mm square. Then we are required the diameter of the spindle. Diameter of spindle. We are required diameter of spindle. And the power is given. Power is already given. So the torque transmitted by the spindle transmitted by the spindle, torque transmitted by the spindle, and the formula is P equal to 2 pi nt by 60. P equal to 2 pi nt by 60. So as per that we can convert it on your T. So T equal to P into 60 upon 2 pi n. P into 60 upon 2 pi n. Then P is already given. It's your 4000. Then 4060 upon 2 into pi into n. N is your 800. Okay, that's why our T torque is 47.74 Newton meter. 47.74 Newton meter. But at that time also, remember that we require the diameter of the spindle small d in mm. So we can convert it that Newton meter to Newton mm. So 47740 Newton mm. It's our T. So T equal to 47,740 Newton. Okay. Then, as per your torsional rigidity, we give the formula related to J. So we know that the J, what is the required formula for the J? J equal to TL upon G theta. TL upon G theta. Okay. Then we require the solid shaft. Okay. So at the time of your solid shaft, J equal to pi by 32 upon d to the power 4. Pi by 32 into d to the power 4. Then torque, right now we are calculating the torque. It's your 47,740. So it's 47,740 into L. L is your 1000 mm. Then require the G. G also put in terms of mm. So it's your 84 into 10 to the power 3. And what is theta? Theta we have converted degree to radian. So it's your 4.363 into 10 to the power 4.363 into 10 to the power minus 3. So we are calculating the in terms of your D. So as per the after the calculating this one, it's 33.93 mm. 33.93 mm. So the diameter of the spindle is 33.93 mm. Okay, now you can check the design data book, and as per your design data book, you can check the nearest highest value of your 33 mm. So as per the design data book, the nearest and highest value of your 33, it's your 36 mm. So from design data book, that is T equal to 36 mm. D equal to 36 mm. Okay. Right now, diameter of the spindle is completed. Then what is the remaining one? Remaining one is the shear stress induced in the spindle. Shear stress induced in the spindle. Shear stress induced in the spindle. Okay, so the torque transmitted by the spindle transmitted by the spindle. So you know the formula related to your torque. It's your pi by 16 tau dq. So T equal to pi by 16 into tau dq. That's clear. But at that time, T is already calculated, D is already calculated. What is the remaining one? Remaining one is the tau, and we are required the shear stress. Okay, so the T is your 47,740 equal to pi by 16 into tau into D. D is your 36. So 36 to, so as per the torque transmitted by the spindle, our shear stress tau is the 5.21 Newton per mm square. 5.21 Newton per mm square. Or we say that tau equal to 5.21 megapascal. 5.21 megapascal. Okay, that's clear. As per the problem, we can calculate the diameter of the spindle, and diameter of the spindle is the 36 mm, and second one is the shear stress induced in the spindle, and the shear stress induced in the spindle is the 5.21 megapascal. Okay, so today's at that time we can stop here. Our today's lecture is completed. Not only the today's lecture, but in your first unit, first chapter, it's your design and shaft is also included. Okay. Within 5 lectures, we are completed our design of shaft. Okay. So, in the design of shaft, first we can discuss about the definitions, then types of shaft, then material used in shaft. Then we can discuss about the 4 types. First was the design of shaft, shaft subjected to twisting moment only. We can discuss about the introduction as well as formula also. Then shaft subjected to bending moment only. At that time also we can discuss about the introduction part as well as the problem also. Then one lecture we can complete discuss about the introduction of combined twisting and bending moment. And the last lecture we can discuss about the numerical on combined twisting and bending moment. And what is remaining one? It's your shaft subjected to your rigidity, on the basis of rigidity. Today we can cover this one, the introduction part as well as the numerical also. Okay, so today we are cover all the topics related to design of shaft. Then after that I will give some problem also. They can helpful to you. At that time only you can learn the design of shaft. But now the time is yours. You all are the practice about the calculating of the problem. I will give you some problem also, so you can solve this problem. That is helpful to you. Okay. So now we can stop here.